Good afternoon, ladies and gentlemen. Welcome to today's Taiwan Bridges keynote speech in Academia Sinica. We are honored to host today's session, which features insights from Dr. Serge Haroche, the 2012 Nobel Laureate in Physics. Before we proceed, the Vice President of Academia Sinica, Dr. Mei-Yin Zhou, will deliver the opening remarks and formally welcome today's speaker. Please welcome Vice President Zhou.
Mr. and Mrs. Haroche, distinguished guests, colleagues, ladies and gentlemen, good afternoon and welcome to Academia Sinica. It is a great pleasure to have you join us today for this special lecture under the Taiwan Bridges program. Taiwan Bridges is an international initiative jointly organized with the International Peace Foundation and designed to connect Taiwan with leading thinkers and Nobel laureates from around the world. Academia Sinica is proud to serve as a co-host for this distinguished lecture series and to provide a platform for dialogues at the frontiers of science and human knowledge. We are truly honored to welcome Dr. Haroche, Nobel Laureate in Physics, who will deliver today's lecture entitled The Laser and Quantum Physics. Dr. Haroche is an exceptional experimental physicist, internationally renowned for his pioneering work that enables the observation, control, and measurement of individual quantum systems. He's the recipient of numerous honors and awards, including the 2012 Nobel Prize in Physics with David Wineland for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. On behalf of Academia Sinica, I would like to express our sincere gratitude to Dr. Haroche for sharing his insights with our academic community and the broader public today. Next, the moderator of this session, Dr. Yu Lin from the Institute of Atomic and Molecular Sciences will introduce Dr. Haroche and his scientific accomplishments. Thank you very much. Okay.
Thank you, Vice President Zhou. Next, we would like to invite today's moderator, Dr. Yu Lin.
Good afternoon, everyone. It's a true honor to welcome today's speaker, Professor Serge Haroche. Professor Haroche is a leading figure in modern quantum physics. In 2012, he was awarded the Nobel Prize in Physics alongside David Wineland for developing experimental probes that allow us to measure and control individual quantum systems, single atoms and single photons, without destroying them. For a long time, these experiments were only ideas in textbooks, and Professor Haroche turned them into reality. Professor Haroche was born in Casablanca and was educated at the ENS in Paris. He trained under Nobel laureate Claude Cohen-Tanouji and later carried out his postdoc research at Stanford University with Arthur Shallow. Throughout his career, he has held prestigious positions at Yale, the ENS, and the College de France, where he served as president. Professor Haroche's major scientific contributions are in the field of cavity quantum electrodynamics, CQED, To explain his work simply, he trapped light between two highly reflective mirrors. He then sends specially prepared Rydberg atoms through this cavity. These atoms act as delicate probes to detect and measure the photons trapped inside. With this extraordinary control, his group achieved several historical milestones. They observed quantum decoherence, watching how a quantum state gradually becomes a classical one. They created Schrödinger's cat states, where light exists in two different macroscopic states at the same time. Most importantly, they proved that we can count photons without destroying them. This discovery forms the basis of much of today's research in quantum computing. Beyond the laboratory, Professor Haroche is also an excellent teacher and author. His book, Exploring the Quantum, is a famous guide to the interaction between atoms and light. We are very lucky to have such an influential scientist with us today. And please join me in warmly welcoming Professor Serge Haroche.
Thank you very much for your kind welcome. It's a pleasure for me to be here. It's the first time I come to Taiwan, and I'm very pleased to have the opportunity to interact with scientists and students here. You know that this year, 2026, 2025 and the transition between 2025 and 2026 is the 100th anniversary of quantum physics. It's in July 2025 that Heisenberg discovered his first version of quantum physics, and in January 2026, exactly 100 years ago, that Schrödinger discovered the famous equation which describes the interaction of atoms between themselves and atoms with light, which is the basis of modern physics and modern chemistry. And so I think it's a very important year to celebrate. And I want to celebrate the laser, because the laser, among all the instruments that quantum physics has made possible, the laser holds a very special place. You see, I'm trying to have this working. Yes, the laser is first an offspring of quantum physics. It comes from the knowledge we have understood about the interaction with atoms with light, but it's also, once it has been invented, it has become an enabler of quantum science that has been, with this instrument, we have been able to do a lot of experiments about quantum physics, which have deepened our understanding of the quantum properties. So I will try in this talk to recall the succession of discoveries which have led to the birth of the laser, which is a tamed source of light. And I will describe some of the breakthrough that the laser has made possible and discuss some of the promises for the future. And in fact, what happened during the last half century is that the laser had fulfilled its promises much beyond our expectation, as I will try to explain. And it also, I think, this history illustrates the deep link between basic and applied science. We all know that the laser is an instrument which has allowed a lot of applications to become possible. The laser is used to read CDs and DVD players. It's used for ranging. It's used in surgery. It's used in a lot of applications. But here I will focus on basics, the application of lasers to basic science. So, in fact, the talk will have two parts. I will first of all recall very briefly how the laser came out of research done in quantum physics before the laser was invented. And then I will, in the second part, discuss what the laser had made possible. So let's start with the laser, the origin of the laser. In fact, the story started even before the year 1925 in what is called the old quantum theory, the first experiments, the first discoveries which have shown to scientists that classical physics was unable to explain the world. And the story started in 1900 and 1905 with the works of Planck and Einstein, which discovered that light, which is supposed to be a continuous wave, is also made of discrete particles, which were called later photons. Planck discovered that because he studied the strange properties of the thermal radiation, the radiation of heated bodies, and he found that to understand the formula which described the spectrum of heated bodies, it was necessary to admit the fact that light was that atoms were exchanging energy with light by chunks, by not continuously, but by discrete bits of energy, which were called photons. And each photon carrying an energy proportional to the frequency of the light, and the proportionality constant is a famous constant, Planck's constant H, which started at that time to play a very important role. Einstein went deeper than that, and he said that it's not only the exchange of energy which were quantized, but that light itself was made of photons, which was a strange concept because the ideas of waves and the ideas of discrete particles classically are contradictory. So you had to find some kind of connection between this wave aspect and the discrete aspects of photons, which is the basis of the quantum theory. A few years later, Bohr used these quantum ideas to quantize the energy levels of atoms. He studied the simplest of all atoms, the atom of hydrogen, and discovered that the energy levels of these atoms were discrete. And to find their values, Planck constant was also important. So it was the first use of these quantum ideas to understand matter. Then, a few years later, Einstein came back to this problem and tried to use this quantum description of the atom to rediscover the laws of thermal radiation. How do atoms interact with light? And he discovered that if you want to recover Planck's formula, you have to admit that excited atoms can be forced to emit light in a stimulated way. A photon impinging on an atom forces the atom to emit another photon which has exactly the same property as the first one. This is called stimulated emission. It is an amplifying process which would lead to the laser after many, many years. So Einstein discovered stimulated emission, and at the same time he had the hint that the photons were undistinguishable particles, because a photon coming on an atom forced the atom to emit a photon in exactly the same state. This idea of indistinguishability was reinforced in Einstein's mind when he received an article written by Bose, who was a young Indian physicist, who used this indistinguishability property to recover again Planck's formula. So the idea is that particles in the quantum world have to be exactly the same. Photons are indistinguishable, electrons are indistinguishable, came suddenly into physics in the 1920s. And Einstein had the intuition to use this property to discover the fact that atoms, as photons, should all come into the same mode at a very low temperature. This was the theoretical discovery of what is known as the Bose-Einstein condensation. At very low temperatures, all the atoms behave as a gas of photons being all in the same state. And so this was at the end of the year 1923-24. At that point, Einstein received the thesis work of Louis de Broglie, who was a young French student. And de Broglie had the intuition that the wave-particle duality, the fact that light was at the same time wave and particles, should also apply to matter. Matter should also have a wave property that, for example, electron in an atom should at the same time have the properties of wave and the properties of discrete particles. And in this way, it became clearer to Einstein that photons and atoms should share this strange dualism. And Einstein, at this point, wrote to Langevin, who was a thesis advisor of de Broglie, "Your student has lifted the veil which hides the mystery of the quantum world." And this is a few months before Schrödinger paper was published. In fact, what Schrödinger did was to find the equation which describes the evolution of the electron wave in an atom. So it's a well-known Schrödinger equation. And I show you here the page of the Annalen der Physik with the year 1926. So it was really the birth of quantum physics that year. So I have recalled here what happened in the in the old quantum theory time. I want to, and all what I have said up to now is theoretical work. But I want here to stress an experiment which was made in 1922 and which plays also a very important role in my story. It is a discovery of two-level systems, the spin of the electron, by an experiment performed by Stern and Gerlach in Germany in 1922. What Stern wanted to do is to measure the magnetic moment of atoms. So it knows that atoms carry small magnets, some material displays this magnetism at a macroscopic scale, but at a micro scale, each atom carries a small magnetic moment. And to measure it, he invented this apparatus that you can see here. You have a furnace, silver atoms are, the furnace is heated, silver atoms are emitted in vacuum, so you have an atomic beam of atoms which cross the gap of a very powerful electromagnet, which produce a magnetic field having a strong gradient of magnetic field. So the idea is that the magnets of the atoms were deflected by this gradient of magnetic field, and on this plate, he expected to see a kind of continuous trace because the projection of the magnetic moment along the direction of the magnetic field could take discrete continuous values. And the big surprise was that instead of a discrete continuous trace, he had two discrete spots. So the magnetic moment of the atom was in fact quantized and could take two opposite values, which later were called spin. The spin could be up or down, but not take any intermediate value when you measure it. This was the first example of what we call in physics a two-level system. The spins represent two possible states of the magnetic moment of the atom in two opposite directions. This is the first example of two-level system in physics, and now this is known as qubits or quantum bits because you can use this system to code information, and so it is the origin of this qubit physics. You see here the trace that was observed by Stern in the experiment, the double leap trace. In fact, this is a spin up and spin down, and the two traces rejoin at here and here because the gradient of the field decreases when you go away from the axis of symmetry of the setup. So this was a very important discovery, and Stern and Gerlach were aware of that because when they did that experiment, in fact, they printed it on a postcard and they sent the postcard to Niels Bohr in Copenhagen just to show that they had observed this phenomenon, and the fact that the momentum of the atom should be quantized had been the starting point of Bohr's theory of the atom. So they wrote here that they congratulate Bohr congratulate you for the confirmation of your theory. And what I want to just say here that this simple split trace announces the 20th century quantum revolution in technology and the qubit in the 21st century. So let's see how it happened. This was the first experiment, but it's important here to state that the next step was taken by Isidore Rabi, who was an American physicist working at Columbia. He was a postdoc of Stern in Germany. It was a time when the physics started in Europe and went to the United States. And now we have more the reverse evolution with a lot of physicists trained in the United States and coming back to Europe. What Rabi wanted to do is to extend the Stern experiment to study the nuclear moments, not the moment of the electron in the atom, but the moment of the nuclei, which is much smaller. And for that, he developed a improved Stern setup. You see now that in his case, the atoms are subjected to two gradients in opposite direction. So the atom or the molecule escaping from the oven were pushed towards one direction here and to the other direction there. So they followed an S-shaped trajectory and were focused on a hot wire on which they lost electrons, and this gave rise to an electric current here, which was proportional to the flux of atoms or molecules reaching the detector. And what Rabi added to the setup, this very important element here, is a cavity in between zone A and B, in which a radio frequency field was applied to switch the spin from the up to the down position. So it's called magnetic resonance. It was discovered by Rabi. And when the flipping occurs, it means that the atoms here will not be deflected in the right direction, so they will lose this trajectory and miss the detector. And if they miss the detector, you see that the signal will decreases when you sweep the frequency away from the resonance. And you see this decrease here. And this was the first magnetic resonance curve observed in 1939, I think. And you see that this Rabi magnetic resonance, in fact, announced the nuclear magnetic resonance imaging, atomic clocks, the GPS, optical pumping, the maser, and the laser. It's the first experiment which shows that magnetic resonance can be detected in this system. And Rabi had the premonition that this could be useful. You see, in 1939, he gave a talk that a journalist was attended to, and the journalist came out with his headline in the New York Post in December 1939, "We are all radio stations, Columbia scientists report." So what Rabi had said is that inside our bodies, we have also atoms and molecules which are able to absorb and emit radiations. And this is an information that maybe one day will be useful. It is doubtful that Rabi had the idea of magnetic resonance imaging, but maybe he had this in mind. But of course, if you want to use nuclear magnetic resonance to detect molecules in our body or the atoms in our body, we should do in a non-destructive manner. You cannot just deposit these molecules on a hot wire. So another step had to be taken, and this step was taken by Bloch and Purcell in 1949 or in 1946, who invented NMR in bulk materials, in solid and liquids. So instead of detecting the atoms, they detected the radio frequencies that the atoms emitted or absorbed, and they were able to do it in a non-destructive way. And after many improvements, it led to the magnetic resonance imaging that we know today. So, and it took something like 30 years from the pioneering work of Bloch and Purcell to become useful in magnetic resonance imaging. At the same time, Rabi had another idea, the fact that magnetic resonance could be used to improve clocks. In fact, in the ground state of some of the atoms, in the fundamental state of atoms, you have a two-level structure. It's called the hyperfine structure, and it happens, for example, in cesium. If the spin of the electron, of an electron in cesium is parallel to the spin of the nucleus, you have one state, and if they are anti-parallel, you are in another state which have different energies. This is called a hyperfine structure, and the frequency difference, the transition occurs at 9.2 gigahertz, 9 billion a period of 92 periods per second. And if you are able to induce this transition, you will have a microwave signal whose frequency will be very precisely known. And for that, a student of Rabi, Norman Ramsey, improved the setup that Rabi had been using. It splits the microwave resonance region in two parts. So the atoms undergo a resonance in the first zone and then a resonance in the second zone. And when you sweep the frequency, you get now a resonance signal which has fringes, which has now a central resonance frequency, which is determined with a much higher precision than in the original design. And so if you tune now your microwave to be at the top of the central fringe, you can lock this microwave very precisely to the frequency of the cesium transition, which is the same for all cesium atoms in the universe. So you get a natural clock which keeps the time with a high precision. This is the origin of the microwave clocks which are used now in the GPS system. The satellites in the GPS system are carrying each clock like this one. They send signals to our detectors, our cell phones, and we are able to localize ourselves, to navigate and localize ourselves with a precision of about 1 meter. So this is another application of this two-level atom physics, quantum physics. Another pre-laser invention is the optical pumping, and I want to mention that because my master for my thesis was Claude Cohen-Tanuji, who was himself working with Alfred Kastler and Jean Brossel in the 1950s at INS in Paris. What Kastler did was to show that it's possible to orient atoms not only by gradient of fields like Stern-Gerlach did, but also by submitting them to polarized light. That the light polarized can exchange momentum between light and atoms, and you can orient all the atoms in a cell in the same, having their magnetic field in the same direction. This is called optical pumping. And this optical pumping has the effect to change the relative population between levels. And in some cases, you can reach a situation where the atoms are very cold. All the atoms are in the lower state, which is a distribution quite different from the ordinary thermal distribution. And Kastler calls that luminous cooling, the fact that you cool matter with light. And of course, this is an effect which became very important later on when the laser were invented. Kastler and Brossel had a young student, Claude Cohen-Tanuji, who discovered the light shifts. He discovered that if light is not exactly resonant with an atomic transition, it cannot bring the atoms from one level to the other, but it can shift very slightly the energy levels. These light shifts are proportional to the light intensity. So if the light intensity is spatially modulated, the atoms are submitted to a spatially modulated force. And this light shift will play a very important role later on for atomic cooling or for quantum non-demolition of photons. And this was 1960. In fact, I joined this group 5 years later, but this history was very important for my training. The last step is, of course, the discovery of the maser and the laser, and this is something which brings us back to Columbia. You see here Charlie Towns and his student Gordon in front of a molecular beam, which is a Rabi machine, at Columbia in 1954. In fact, what they exploited is the fact that the ammonia molecule is a two-level system. You see formula for NH3, the nitrogen atom can be either above or below the plane of the hydrogen, and it flip-flops by tunnel effect across the plane. And this flip-flop is due to the fact that you have two-level system, the symmetric and antisymmetric superposition of these states. And if you prepare the atoms in the upper state, it will go down by stimulating emission of radiation. And if you have a cavity which is tuned to the right frequency, you will have amplification. And this is, of course, a maser. Now, once the maser was invented, the next step was to extend this to the optical domain. It's a story that I don't have time to talk about, but a few years later, Theodore Maiman in the United States was able to build the first amplifier of light using this principle of stimulated emission. And this was the birth of the laser. So this is the end of the first part of the talk. You see that this long lineage of discoveries and experiments which led step by step to the laser. So I go now to the second part, laser powerful enabler of breakthrough in quantum physics. The laser is, of course, a fantastic source of tame light. It's intense, it's directive, it's monochromatic, and it's coherent. Of course, at different levels, depending on the laser that you have built since then, you can emphasize one of these properties and to have it extremely precise. So what can you do with the lasers? It's very difficult to summarize everything, but if you use the intensity and directivity of this emission, you can reach very high temperature. You can ignite fusion and evaporation of matter. You can even reach temperature high enough to induce fusion of atoms, and this is one way of research towards the fusion, which will be a source of energy. And at the same time, the laser can also achieve the lowest temperature existing in the universe. If you are able to send light in opposite direction so that the atoms will absorb the momentum from all directions, you can cool the atoms to extremely low temperature. So you see, you can go from temperature as high as the one existing inside stars to temperature of the order of 1 nanokelvin or even less, which are so cold that then the Bose-Einstein condensation that Einstein had imagined 1 century ago become possible, and you can reach this temperature which allow you to study phases of matter which don't exist in nature, but can exist in laboratories. So that's one part. Now you have also all what you can do to exploit the monochromaticity and the coherent properties of radiation. You can have, if you have a monochromatic beam of atom propagating over very long distances, the coherence, the laser beam does not skip a bit over millions of kilometers, and you can do interference experiments by reflecting back the beam with a mirror. You can do fantastic interferometric experiments. You can also generate laser beams which oscillate at frequencies which are separated by equal distances. So it's called a frequency comb. And this frequency comb is such that the light becomes very intense at very short times and disappears and comes back at a later time. You can make very short pulses of light, very intense and short pulses of light, and reach in this way extremely high energies for very short time and extremely short pulses, pulses which last only a few attoseconds. An attosecond is a billionth of a second. You can do with this kind of light study very fast processes occurring in atoms, in molecules, or in solid state systems. So you have a tool to study very fast processes in physics, chemistry, and biology. So to summarize, you can do a lot of fundamental research in this field, and you can also, of course, have a lot of applications. But here I want to stress the orders of magnitude. I want to recall you here that the laser has made tremendous progresses possible and has led to qualitative and quantitative evolution in basic research. For that, I will show you here that you have more than 10 orders of magnitude, factor 10 to the 10, improvement in many fields. And to reach a factor 10 to the 10 in 50 years means that, in fact, you reach a factor of 10 every 5 years or so. And I think this is a fantastically fast process. If you think that a PhD lasts at least 4 or 5 years, it means that the student coming into this field, in one generation of students, the technology has changed by 1 order of magnitude. So it opens a lot of, it's a big challenge to keep track of this evolution, and it's also a big promise for future application. So I'll give you a few examples. I compare here what you could do in 1960 and what you can do now. The temperature, 50 or 60 years ago, a cold 1 Kelvin was supposed to be very cold. And all physics occurred between 1 Kelvin and 300 Kelvin. Now we can go to 10 - 9 Kelvin and even below. So it's again something like 10 orders of magnitude, and a lot of things come from that. The precision of clocks in 1960 was 1 part in 10 to the 8. 10 minus 8, it's about, if you count, it's about 1 second per year. And now with the spectroscopic progresses, we have now reached 10 minus 19, 10 minus 20, which is better than 1 second over the age of the universe. And this is a big progress in the precision of clocks, which we have, which are due to, especially to the laser, because now these lasers are, these clocks are optical clocks which are locked, which lock a laser to an atomic line. The sensitivity of measurements, the optical pumping experiment I talked to you about before, we're measuring signals in cells containing billions of atoms. Now you can work on a single atom and at a single atom, single photon level. The speed and time resolution, the shortest pulses you could do with sparks or classical light were the range of microseconds to nanoseconds. Now we are in the attosecond regime. And the last example I take here is the sensitivity to lens variation. Before the lasers, just before the lasers, the meter was defined by a Michelson interferometer locked on a krypton line transition. The interferometry definition of the meter is precise at a range of 10 minus 8 to 10 minus 9, which means that you knew the meter to 1/100th of a micron, which is already very precise. But now with big interferometer like the LIGO and the Virgo one, we reach a precision which is able to measure a difference in length in the range 10 minus 21 to 10 minus 22, which is the precision required to detect gravitational waves. So again, an improvement at more than 10 orders of magnitude. And since this is maybe the most spectacular achievement, I just recall you here the first signal of a gravitational wave, which was detected 10 years ago. It's the coalescence of two black holes, which are 1.3 billion light years away. They end up their life by spiraling around each other, and then they collapsed. And at the last second of the collapse, they send a gravitational wave, which reached the Earth 1.3 billion years later. And you see the signal in red and in blue are the signals which have been detected by the two antennas located in the United States, in Washington State and in Louisiana. And of course, you need at least two antennas to make sure that what you observe is not an artifact, that it comes from the same source. And this signal is exceedingly small. In fact, this oscillation is not, it's in fact the shortening of the length in one arm and the dilation of the length in the other arm. The arms of the interferometer are 4 kilometers long, and the change in length is about 10 billionths of an atomic diameter. So you take one atomic diameter, which is 1 angstrom, you divide it by 10 billion, and you have the change of length that you are able to detect with the system. So it's a fantastic tour de force, especially if you think about the energy which was released by this, what happened here. These two black holes, the coalescence of two black holes, resulted in a loss of something like 5 or 6 solar masses. So 5 or 6 solar masses have disappeared in 1 second. If you compare that with the energy that the sun is delivering 1,000th of a solar mass in 5 billion years. So you look at the orders of magnitude here, and the result is so small that Einstein believes that it would never be observable. And this is due to the laser. Without lasers, you will never have seen that. And this is, of course, the beginning of a new physics. These gravitational waves are a new window into the universe. So it's again, it gave rise to a Nobel Prize. A few words about laser cooling. You see here a picture where we have 6 laser beams which are focused on a spot where atoms are kept in a well-defined location by these laser forces. And you have about here about 1 billion atoms at the crossing here. You have about 1 billion atoms which have a temperature of about 1 microkelvin, which intersect at the, so it's already very cold, 1 microkelvin. And in fact, to understand this cooling process, it's a very sophisticated, very subtle process. In fact, it's related to light shift effect. In fact, at the intersection of the light laser beam, the light beams interfere with each other and give rise to potential, to a modulation of the energy landscape. And you see that the energy that the atom have to face, the potential energy is modulated, and it's modulated in opposite direction, taking opposite value, whether the spin is down or up. So you see what happens, that the atoms are climbing hills, losing energy, and then by optical pumping, they are reset into the lower state, and they have to climb and lose energy and so on. So it's like Sisyphus in the Greek mythology. The atoms keep losing energy more and more as the process occurs. This was explained by Claude Cohen-Tanuji at the end of the 1980s, and the process called Sisyphus cooling, which leads to this extremely low temperature, which are much lower than what you would expect from a simpler explanation. And when you reach this kind of temperature, if you go a little bit further by a process called evaporative cooling that we don't have time to discuss, you get into the degenerate gases that I was talking to you before. The atoms are so cold that their de Broglie wavelengths becomes large, and they all collapse in the same quantum state, indistinguishable particles, which are in a state which recalls the properties of photons in a laser. And in fact, you can, if you let this atom escape from the Bose-Einstein condensate, you get a stream, extremely well-collimated stream of atoms, in which atoms are replacing the photons of a laser. So you get atom lasers, in fact, in which have a long coherence, and a lot of physics is being done now with these systems, which are the coldest system you can think of in the universe. The next thing I would like to talk to you about are the progress of optical atomic clocks. As I said, you can now lock a laser to an optical transition. The uncertainty has become of the order of 10⁻⁹, which is about 1/20th of a second over the age of the universe. This is 100,000 times more precise than the GPS clocks. So if you look at the history of clocks, in the 17th century, the first physical clocks were the pendulum clocks. They had a precision of 1 part in 10 to the 4, which was about 10 seconds per day. Then there was a big jump with microwave clocks by 10 orders of magnitude 40 years ago. So 10 orders of magnitude in 300 years. And in the last 40 years, we made another step of 5 orders of magnitude because we went from the microwave clock to the optical clock. And these clocks are so sensitive, so precise, that the time does not elapse at the same rate at the top and at the bottom of the clock. A difference of 1 millimeter is observable. So it means that these clocks are a little bit like the soft clocks that Salvador Dali designed in the 1920s to illustrate general relativity. And what I want to stress is that the laser is essential in 4 different ways for these clocks. First of all, you need lasers to cool the atoms, to stop them in their motion, to make sure that you have no Doppler effect. Then you need another set of laser to trap the atoms, to hold them at well-defined position in a kind of optical lattice, like the one you can see here. So this is the second laser. You need a third laser system to excite the strontium transition, a very precise laser to be exactly on top of the transition. And finally, you need a frequency comb laser to transfer the frequency stability to the microwave domain. That is a laser which one mode of the comb is locked on the optical atomic transition, and the separation between successive modes is an exact divider of the optical frequency on which you can lock a microwave clock, which is necessary if you want to count, because you have electronic devices who can count microwaves, but not electronic devices to count optical systems. So you need 4 different lasers. So it's really a triumph of this laser technology. And you can still hope to increase the precision if you entangle the atoms with each other. You have more precision, and you can go to higher frequencies if you build laser combs working in the ultraviolet and lock it on a nuclear transition. So there are still hopes to get to much higher precision, and then you can start to look at processes involving general relativity in a new context. The last point I would like to stress is, of course, more closely related to my own research, the fact that you can observe and manipulate non-destructively single atoms, molecules, and photons. And in fact, this is related to the work which is being done in ion traps by Dave Wineland, which shared the Nobel Prize with me and other people. You see here, for example, 54 calcium atoms which are held in a linear trap. Each atom fluoresces, is separated by a distance of the order of 1 or 2 microns from its neighbor, and it makes a big abacus on which you can do some kind of quantum computing. Each atom fluoresces in one quantum state, not in the other, so you have a kind of qubit, and you can, with lasers, interrogate these qubits, entangle them together, and build what is called quantum gates, and look to demonstrate elementary steps of quantum computing. So in this experiment, what you do is that you trap the atoms and control them with light. What we do in Paris is the opposite. We trap photons inside a cavity, and we interrogate them with atoms. So you see the setup here. You have here the cavity, which is made of 2 very well-reflecting mirrors. Microwaves are here, and Rydberg atoms which are excited into a very excited state, cross one by one this cavity. These Rydberg atoms are very sensitive to microwaves, which makes them undergoing transition from one state to the other, and they are interrogated here, detected here by an electric field which breaks them. And this is the Ramsey setup. You see the atoms, before they enter the cavity, they are submitted to a first microwave pulse here and to a second pulse here. And we look, like in an atomic clock, we look at the transition between the 2 states, and you have fringes when you sweep the frequency, exactly like in the microwave clock. But you see what we do here is that we set up so that the frequency of the photon is slightly different from the frequency of the atomic transition. So there is it's a non-resonant situation in which you don't have transition between the state, but you have light shifts. And the atoms are so sensitive that a single photon shifts this set of fringes by just half a fringe interval, which means that if you set up the frequency here, the atom will get out of the system in one state if you have 0 photon, and the other state if you have 1 photon. But the photon is not absorbed. The photon is just used to force the atoms to be detected in one state or in the other. And so in this way, you can build a system in which you detect the photon without destroying them. You see here for a long time, there is no photon in the cavity. Then 1 photon appears spontaneously. A lot of atoms detect the same photon until the photon disappears. And you see the quantum jumps when the photon goes from 0 to 1, or from 1 to 0, and you see that hundreds of atoms see the same photon, which is quite different from the photoelectric effect or from the ordinary vision in which the photons are destroyed. So this gives rise to a lot of experiments in cavity QED that our group did, and it's an effect which is widely used now in circuit QED, in which the real atoms are replaced by superconducting circuits, and the generalization to circuit QED has been recognized by the Nobel Prize last year in 2025 to people working with superconducting qubits. So the last point I would like to talk about Rydberg atoms is the fact that they are not only useful because they strongly interact with microwaves, they're also useful because they strongly interact with each other. They're like big antennas, And you see here the main effect, which is used in this experiment, is called the dipole blockade effect. You see, if you focus, if you make now a trap with two very close potential wells here, and if you trap one atom in each of these potential wells, the atoms are trapped in their ground state, and you try now to excite them into a Rydberg state. If you excite one atom, then the other atom would not be excited because it is shifted by the first big atom. So two big atoms cannot be excited by the same laser beam because each atom is shifting the energy level of the other. So this is what happens if you try to focus the laser beam on one atom or the other. Now, if you try to excite the two atoms at the same time, the same effect occurs, and you can excite only one excitation, and the second excitation becomes shifted by the dipole effect. And so the result is that you have one excitation, but which is evenly shared between the two atoms. You excite a superposition in which either the first atom is excited or the second. And this situation is an entangled state. It means that the two atoms are correlated, have a quantum state correlated to each other in a symmetric way. And this is a way to build quantum gates, to build system in which one atom controls the state of the other. So entanglement and gates have been studied with the system, and you can now, by focusing the atoms at different points in space, realize lattices in which you force the atom to interact in this way, and this is the domain of quantum simulation. You can simulate ferromagnetic and antiferromagnetic materials, and you can also use this kind of system to do the research on a quantum computer. In fact, there is a lot of research being done along these lines in the United States, in France, and other parts of the world. I want also to stress that the lasers have extended the notion of entanglement and non-locality from nanometer to thousands of kilometers. Schrödinger famously said that entanglement is the essential feature of quantum physics. And what he had in mind is the fact that even the simplest of quantum systems, like the hydrogen atom, the system is entangled. The nuclear and the electron spin in the ground state is an entangled state of the two. If the spin of the nuclear is up, the spin of the electron is down, or the opposite with a minus sign. This is an entangled state, but which has a size of about 1 angstrom, which is the distance between the electron and the nucleus. Now, we can do experiments in which this entanglement is carried at macroscopic distances. These are experiments that Aspect did in Paris in the 1980s. He showed that entanglement survived at 6 meters in his lab, and now we know that entanglement can survive over kilometers, or hundreds of kilometers. This is again made possible by the lasers. I will skip this. In these 3 slides, I just explained that how you can do attosecond physics with lasers, but I think we don't have time. And the last point I would like to stress here is that the laser spectroscopy can be used to search for new physics. There is a series of experiments which have been done in many labs now, several labs in the world, which are looking for an electron dipole moment, that is a dipole moment of the electric charge inside an electron. According to the standard model of quantum physics, the electron is a point charge, it has a spherical symmetry. So there is a charge, but no dissymmetry in the charge distribution, no dipole. But there are some extension of the standard model which predict the existence of supersymmetric particles, which would give a very small magnetic moment to the electrons that you can interpret as a kind of non-spherical charge, a kind of oblate or prolate charge distribution. So the question is the electron exactly spherical? And what the theory says that the standard model predicts that the electric dipole moment should be smaller than 10⁻36 electron centimeter. This is very, very small, and this would be due to the fact that the violation of time reversal symmetry, according to the standard model, is exceedingly small. But if you accept the possible existence of supersymmetric particles, then you can imagine that the electric dipole moment should take a value between 10⁻31 or 10⁻32 electron centimeter, and this is what people are looking for, and this is also very, very small. So how do you do that? It's again a kind of Ramsey experiment. You are looking at the spectroscopy of an electron which is embedded in a molecule. It should be a molecule which has a very large electric charge for the nucleus, because in fact what you have to do is to reverse the electric field. You are in a magnetic field, you look at the precession of the electron spin in a magnetic field, depending upon whether you have an electric field parallel or anti-parallel to the direction of the magnetic field. But this effect is so small that you need a huge electric field, which is not possible to get by just applying the field by electrodes. What you need to do is to enhance this field inside the molecule due to the fact that the nucleus itself has a very high electric field gradient. And so you do this experiment and you look at Ramsey fringes. They don't have time to give details, but the precision of present experiment is about 4 × 10⁻30 electron centimeter. At this level, nothing has been found, but there is a hope that with 1 order of magnitude more precise experiment where we find something. Just to stress how small this is a defect of sphericity of 1 part in 10⁻17, because you can assume that the electron has a dimension of about 10⁻13 centimeter. This, if you blow this up to the size of the Earth, if the electron was the size of the Earth, this delta R over R would mean that delta R is 0.1 nanometer. So you have a defect of symmetry, which is about the size of an atom over the size of the Earth. So it's really a very, very small effect. But if you refine this effect, it could be an evidence of new particles, maybe something which has to do with dark matter, with important implication for quantum physics and cosmology. So I'm here coming at the end, but I want to stress that the spirit of these experiments is very close to the spirit of things which have been done by scientists a long time ago. In the 18th century, the question was not, is the electron spherical? Nobody knew about the electron, but a similar question was raised, is the Earth exactly spherical? And in fact, there was some hints that the Earth was not a sphere because of the rotation induced a centrifugal force which were making the Earth oblate. And there was some hints of that because pendulum were beating slower at the equator than at northern latitude. And to test that, expeditions were sent at the North Pole and the equator to measure the meridian and to see whether it was a sphere or not. These are experiments which were as expensive and as long and as difficult as the one I am talking to you here. And they were much more dangerous because a lot of people lose their life in doing this. But the spirit was the same. The spirit was the same, trying to understand something out of curiosity and using the most sophisticated tools that were, at that time, the sophisticated tools were telescopes, which were able to measure the position of stars with a very high precision, and rods, which are able to measure distances, which were not sensitive to dilatation or due to temperature. And so it was really the same spirit. And of course, it showed that the Earth was indeed oblate. So I just want to conclude here by trying to stress some important point. First of all, I hope I convince you that the laser is important in basic science. Also that lasers have in fact inherited many tools invented in optics and atomic physics before lasers. I talked to you a lot about Ramsey fringes, which were before the laser, about Stern-Gerlach kind of experiments, which were discovered and invented before the laser. So it's, in fact, each generation of scientists is building up upon the heritage received from the previous ones. I think also that the passion for precision is at the heart of the scientific method. Each time you invent a measurement device more precise than the previous one, you discover new effects. I hope also that other breakthrough can be expected in quantum physics and maybe in cosmology, where laser will be useful again, for example, in increasing the precision of clocks, and also stress the deep connection between basic science and technology. And since this series of lectures is focusing on Nobel Prize winners coming here, I just show you here this list showing that since 1965, 43 Nobel laureates in physics and chemistry used lasers for their discoveries. And you see that it was important for physicists, but also for chemists, and maybe also for biologists. And the last one was given in 2023 for attosecond physics. And I am sure that there are more to come for some of the development I talked to you at the end of my talk. Atomic clocks, symmetry breaking in atomic physics, all this is certainly a domain in which you will have Nobel Prize in the future, and maybe in other fields we cannot even imagine today. So I will stop here and thank you for your attention.